José?
Thank you very much for the everyone. My name is José Claudio. I'm from Brazil. I'm the master student at State University of Campinas. In this presentation, I will present instrumentation work that I have done in order to apply a magnetic field with temperature in the sputtering deposition system. This work has the motivation to better understand the fundamental and applications of magnetic films that has a sort of a lot of several applications in spectrometry, magnetic sensors, magnetic recording medias, and in order to improve this all these fields, we have a lot of possibility to improve in the position of these thin films. In this particular work, we are focused on magnetron sputtering, where it's widely applied and has a great interest to upscale the productions of thin films. And in this work, we are interested in from the several variables that are available in the sputtering system. We are interested in the to attack external magnetic fields with substrate temperature to understand how the magnetic fields in different directions when applied during the sputtering deposition can influence magnetic and structure, and while all the others variables are keeping the same. So in our sputtering system, we had a target and a substrate and a rotating plate with heating lamp to increase the temperature. So what's the instrument challenge? In this rotating plate sputtering systems, we have a rotating plate, quite constrained dimensions. It's worked in high vacuum, and we need to apply temperature up to 300 Celsius. So for the solutions that we think about is to use the permanent magnets that's totally compatible with high vacuums, and it's great to produce high magnetic fields in constrained dimensions and it's easy to produce a small magnetic permanent magnets. And for a rotation plate, it's perfect because you don't have wires to entangle everything. And to apply temperature up to 300 Celsius, so the system could be possible to be versatile to the position of several alloys that have phase transitions or structural transitions with temperature. We choose to use samarium cobalt alloy as our permanent magnet, because this alloy had a working temperature up to 300 Celsius and a nice flux. From the deposition plate, we designed three positions, three different arrays of magnetic fields. One in plane with the film. That's this in plane film. We used a Halba array it's quite good for our system because it has a uniform and intense magnetic field inside the array, and the external magnetic field is shielded, so it's not influence the others. So we perform 3D simulations with syn-center magnets to preview what the field that you could reach. So this is from the in-plane field, and for the out-of-plane simulations, we designed three different geometries. One with cubic similars from the previous one, that's 1 by 1 centimeters cubes, when the magnetic fields align perpendicular, and the other with a donut shape. One's a completely round donut shaped, and the other with optimizations, so you could reach higher magnetic intensity only in our interest region. So doing the simulation, we choose the third geometry, so that's the best one that you can keep up with the same magnetic field as the in-plane array. And from the third deposition region, we choose a minimum field setup, like a shielded field, where we can study the film without the influence of magnetic fields, so you can compare the three of them. For that one, we simulated with the complete array of in-plane and out-of-plane magnets in the region with no shielding, and one with a shielding with the donut shaped geometry made of carbon steel. So we concluded that with the shielding we have almost 5 orders of shielding magnetic fields. So it's quite effective to use it to have to minimize the influence of the other one, since the size is really constrained. Well, once we did all these simulations of the magnetic field, we also wanted to measure with a gaussimeter to characterize the field, the magnetic field. So when we simulated for in-plane and out-of-plane around 0.46 Tesla from simulations, and from measurement, we got quite similar from what we expected. And for the shielded field, we also could conclude that it's really shielded the external field. So as a proof of concept, we put it inside the chamber and did the first co-deposition of iron platinum with temperature of 250 Celsius. We deposited thin films of 40 nanometers and a cap layer with of gold with 5 nanometers. And after that, after the deposition, it proved that this work with temperature, because after the depositions, the magnetic field continues the same, so we've not had any problems with the magnetic field was constant along all the depositions. And since it's we observe some disturbance in the plasma inside the chamber, we did measurements of EDS and X-ray reflective to see if in each site of the deposition plate would have the same amount of iron and platinum, and the thickness of the field, the film was affected by the field. So from the energy dispersive measurement, you can see that we have the same amount of iron and platinum in this co-sputtering deposition in all the sample positions. And when we treated the X-ray reflective data, we could see that our thickness reached was quite close from the nominal one, but we can see a deviation less than 10% of the thickness from one side to another. And from the gold cap layer, we can also see a deviation of around less than 10%. And so can conclude that the film has almost the same thickness, and the further studies that we need to do is to better understand if this magnetic field has some influence on this on the structure or the magnetic response on these films. But it's the biggest conclusion that we can have is that the instrument could apply two different magnetic field directions, and one with minimum fields all together is in the same sputtering round. And it's also interesting because it's a model setup, so you can change the model according with your interest. If you have two in plane or two out of plane difference one, we can move it. And it's compatible with the temperature. The characterization of the magnetic fields was comparable with the simulations that we had. And we successfully grow a first round of thin films with it. So I want to acknowledge all the institutions and the founding agents, and thank you all for the attention. Thank you very much.
Thank you so much, Jose. We very much appreciate your talk. And Fen Shu has a question.
Thank you so much. This is very interesting work. So just a quick question. So about the magnetic field, I think the purpose is to induce the magnetic anisotropy during the sputtering. So do you think this, if you're, for example, if you're sputtering a non-magnetic material, do you think this magnetic field will induce some certain direction of texture to make the growth of the texture different?
Yes, I think that's it's possible, because I already read in the literature that depend on the magnetic field applied in this specific case of iron thin films, it can affect the texture. So I think that's this setup probably will have a different texture of diffraction, the texture of different from the out the plane from the in plane. I think that can be it should be possible.
Yeah, thank you. If this is very significant, I think it is very useful for the future when we do some special texture or crystalline for some unconventional purpose. Yeah, thank you.
Yes, I think that's quite possible. Thank you very much.